Okay, property sheet. Goal today is to actually walk through what each of these are. I think it's important that instead of just giving you crash courses and then just throwing you in the deep end and saying, hey, this is the property you use, and you're like, I didn't even know that property even existed. Let's go through what each property is, what the name is, what it actually entails, how do you use it. So it's going to be kind of a lengthy day. Sorry, it's one of those days we just have to get through some notes. And then tomorrow we're going to really look at doing kind of more hands-on, where I give you a problem and we really kind of work our way through it systematically. Tomorrow you'll probably, I would expect a homework assignment of probably about 4 problems. Not joking, about 4 problems in your homework tomorrow.
But we'll have to show all the work.
So, yeah, you have to show work, and it takes a while, so that's why I'm not giving you a lot. It's just one of those things like you just need practice at. You need to try it by yourself, but we need to get to the point where you're comfortable doing that. So right now, I'm sure that you're not. So we need to like go through the property names so you kind of understand what they are, what they entail. So that way tomorrow when we start actually working on problems for the first time, you're like, oh, I remember that property. We talked about it, Tuesday. So the properties of equality. We talked about these yesterday. What do you use these properties of equality for? What type of problem?
Problem with the equals.
Has to have an equal sign. Has to be an equation only. That's good thinking. So has to be an equation only. So I'm going to put that right here. You don't need to write this down. I'm just kind of reminding you of that. When you use these properties of equality, they have to have an equal sign. If your problem doesn't have an equal sign, you probably won't use any of these. I'm not even joking. None of these properties would be used. You just go down to the field properties and you'd simplify from there. But these are a setup. It sets up your problem so you can solve it later. Usually what you do is you do about one of these. That's it. You do one of these properties and then you go down to the rest of like down here and you do the field properties for the rest of it. The field properties are the actual properties used in the field that you actually solve a problem. You're actually doing the dirty work. But the properties of equality is just that first step you have to do. Or maybe it's one of the steps. Usually you do it once, usually, if it's an easy problem. But let's talk about what each problem is. So let's kind of go through these systematically, kind of one at a time, so you kind of know. So if you have your notes out, it'd be kind of a nice thing that you can write down the property name and then put very specific examples underneath each. I know that on my little property sheet, I do provide you with something very, very, very generic, but I want you to really understand what each of these are. Reflexive property. Let's start there. So the reflexive. Okay, the reflexive property is anytime I write a problem on the board and you copy it exactly 1 for 1, or if I told you 2 things were exactly equal to each other and you set them equal to each other. So let's say, for instance, I said that, maybe the formula for age is, let's say the formula for age is this. That's your example. That's the formula for age. And your age is 16. Well, then what you can do is immediately set things equal to each other. That's reflexive. You're setting something equal to itself, and you're setting up your problem for the first time. Maybe they tell you 2 things. Okay, so it could be something really similar to that where I give you 2 parts, you set them equal, maybe you just notice that type of thing, or maybe it was like 2 angles are adding up to be this. So in your problem, so you'd add up, whatever the 2 angles are in your problem, and you know that it was supposed to make 90, right? You're setting up your equation for the first time, where reflexive means one thing is equal to another. Okay, it's just a generic setup. So that's what you're seeing here. Now, to be super specific, where I actually would use this for the first time, it's copying down a problem and it's setting equal to itself and then working with one side and simplifying one side. That's where I use it. So I know it seems really goofy, but it's like when you write notes for the first time, some people are like super organized about their notes. Let's say a problem looks like this. And what I would do is I would set it equal to itself, and I'd work with one side only. I'd work with one side and I would simplify one side out and, you know, see what it actually turns out to be. That's something I would use it for, but that's not a true property of equality, right? I'm just working with one side only, kind of seeing what adds together. It's more of a note-taking process. That's where I use it, but it's anytime you just set an equation up, you set something equal to something. It could be just the start of your problem. That's why kind of like my first hint to you was, if you just took a problem that I had written on the board and you copied down into your notes, you just did the reflexive property. You just copied it, you have an equation set up, something equal to something. Okay, questions with reflexive. Typically, I don't use that property name a lot. I'm sorry, I just don't. Okay. Let's do symmetric. This is the symmetric property is one you actually use a lot in Algebra 1 class. It's one that I found that, I don't know why, it's just it's this weird thing that I guess my teachers kind of really kind of hammered it in to my head where, you know, let's say you had a problem that looked like this. Let's say that was your problem, right? Some people, like when they see that, they get kind of unnerved by it. The symmetric property allows you to take this equation and you can switch the right and left side. The right and left side, you're allowed to just switch these automatically across an equal sign. That's symmetric. So I can take and I just keep them exactly the same way that they're written, but I just flip their sides. This is still the same problem. It still has the same answer. That's what my math teacher always, you know, kind of beat into us a little bit was the variable should always be on the left side. And then you should always do the work that you're doing and you solve it. It doesn't actually matter. Some people don't care. Like some people are really good about just solving where the variable is. They don't really mind. But some people are like super strict. Like I don't know why, it's just this weird like quirky thing where you have to have the variable on the left. Okay, does everyone understand what symmetric is? Sometimes it is helpful just to get it switched around so it looks better. But notice, the weird thing about this, I moved everything from the right to the left side, right? I moved them. But nothing changed signs. Like nothing went negative, nothing went positive, nothing. It's because everything
moved.
And that's why you don't need to switch the signs. Because if you switch signs, everything would turn out to be negative and still be the same answer anyway, so there's no point in switching all the signs. So that's symmetric property. It's useful to a point. You don't necessarily have to do it. I don't know, it's a weird thing for me. I like to have it like written like this. I don't know why. Transitive property. Now this is the one that I was kind of hinting at earlier. Transitive is this weird process where you have a problem and you're going to figure out a solution to it by using logic. Okay. So here's the best way I can describe it to you, and then I'll show you an example like with algebra. Okay. So let's say, and I'm going to make up numbers here. So let's say Gouge. I'm saying you're the same age as Vanessa. Okay. So Gouge is the same age as Vanessa. And Vanessa, you're the same age as Cody over there, okay? Cody, how old are you?
15.
15, okay, let's just say that. It doesn't matter if it's right or wrong. So you're the same age as her, you're the same age as Cody. So, and you said you're 15, right?
Yep.
So how old is Gouge?
15.
That was transitive. You just did transitive. Because I didn't tell you how old she was, right? You agree? I didn't say her age. I said you're connected to her, and you're connected to him, and your age was 15, and you connected the dots. That's transitive. Connecting from the beginning to the end, but it's just doing it logically. You knew that you could transfer stuff, okay? It's very similar to when you guys are doing the bobsled problem, the bobsled, right? You're trying to figure out the mixed pairs. You had to take a lot of clues and connect the dots, even though I didn't explicitly say it out loud. You had to know that that was true. Okay, bless you forever. So let me show you an algebra problem, because obviously that idea of age makes sense, but when you actually see it in an algebra problem, you're like, oh, well, yeah, okay, that works. So this is the way that I'll just show you that one problem I wrote down earlier. So again, this is transitive. Okay, so let's just say there's the 5a plus 6 minus 7a. I don't know if this is a plus 10 or something like that. I don't know what I wrote down earlier. Minus 7a plus 10. Okay, so let's say that was my problem, right? This one I wrote down earlier when I did reflexive. And over here, I can like add certain things together, right? I don't care about this left side. I'm going to leave that alone. What can I add over here on this side? Okay, 6 and 10, so that makes 16, right? And the 5 and the 5 and negative 7 makes it what, negative 2a?
Yep.
Okay, if you did all the correct work, so there's a bunch of work that happens in there. I skipped a lot of steps, sorry. Okay, so we agree that like this is what it comes down to after I do a bunch of steps. right? It works out to be that, because you'd have to move things around, and there's a bunch of other property names. Well, I could have just wrote this. And this would still be the same problem. Still the same problem, because I knew that that side simplified, so whatever I started with, I could have just wrote it what it was equal to eventually in the end. That's transitive. You connected the beginning of your problem to the end of your problem and said, oh, they're the same thing, they're equal to each other, which they are. They are still equal. It's this weird thing you can connect the dots. This is how people like try to justify their work. When I show them like an algebra 1 problem, they're like, well, the answer is 2. Well, I just know how to do it. It was common sense. Because they're doing transitive in their head. They're just like, well, that's the only answer that exists. That's the only thing I know. But you missed all the work in the middle. Transitive just connects the beginning to the end of the problem. It skips all the important stuff in the middle. So sometimes it's nice to know that you know what the answer is, and then you can start to fill in the gaps later. Okay, questions what transitive is. Beginning to the end of the problem. Okay. Sometimes it's useful to show what you started with and what you ended with. But it's usually when you're simplifying, you're not really solving anything when you do that. Okay, now, the last ones. Okay, so, all right, for the last ones. Okay, so addition, multiplication, subtraction, division, no particular order. I just wrote those in there. I just kind of spread them out. These are the properties we call it. Each one of these things would actually be the reflexive property of equality, symmetric property of equality, addition property of equality, right? The properties of equality are something you do to both sides of an equation. So everything I've done up to this point, I've done it to both sides, equally. If I flip things around, I did it to both sides. But the addition property of equality is the same thing, or multiplication. So let me just show you what I'm talking about. Somebody give me any number you want. Just make up a number.
8.
8. Okay. 8. What property allows me to write that? Reflexive. I said something equal. I set an equation up for the first time. Something's equal to something. I agree with that, right? It's reflexive. What these other ones allow me to do is do anything I want to both sides. Anything I want, right? So I can add numbers, I can subtract numbers, I can make up a number for all I care. I could add 20 to both sides. And it would still work, right? This would actually work out to be, 28 equals 28, right? Do you agree 28 is still equal to 28? Right? It's still a balanced equation. Right? The weight's still the same. You add weights to both sides of the scale, it balances out the scale. This idea, what you just did here, where I just showed what I'm going to add to both sides, that's the addition property of equality. Addition prop of EQ. It's not the answer. I don't care about the 28s. It's the simple fact that I'm showing my evidence of what I'm going to do. Where I'm going to just magically add 20. Now you guys have learned algebra 1 problems where, if they gave you a problem like this, let's say that was your problem, you guys have been taught, programmed to solve that thing that you need to get rid of the 4, right? Because I want to get the x by itself. So how do I get rid of the 4?
Add 4 to each side.
Exactly. And that's that simple fact that I'm just showing you that, the work that I'm about to do, that's a property of equality. It's this property. It's not the answer. I don't care about the answer. It's the simple fact that I just showed, I'm going to add 4 to both sides. You can do that to any equation because as you saw there, from that crude example I made up, you can make up any number you want. I could add 20s. I could have added 15s to this problem. And the answer would still be the same answer. They just taught you in Algebra 1 to be very specific on which number you should choose to add, because you can add anything you wanted. So they just teach you, you should always pick the number that's on the side with the x. Pick that number, and just always pick the opposite of it, and add it to both sides. All right. So even if this was a, if this was a plus 4, you're still going to add a negative 4 to both sides. You could add the opposite number. Because what will happen is that these will eventually go away. That's the addition property of equality. Now it's better known as subtraction if you want to use negative numbers to subtract both sides. So, okay, do we understand how those little properties work? Now, my math teacher in school did something extremely cruel. Okay, I'm not going to do that to you because it still makes me mad to this day. That's how cruel it was. So, all right. So this is the problem that she had set up at the time, just to prove her point. Okay. All right. So do you agree 10 is equal to 10? Okay, so the example she used in class is we had 20 kids in class, so we separated our class to be 10 over here, 10 over there. She just told us to separate. And she set up desks in the middle to make an equal sign. So 10 kids and 10 kids. And she goes, okay, the property is equality. Whatever I do, I have to do it the same to both sides or it's not a fair concept. And she did this at the end of class. So she goes, okay, so you can do any of this stuff. And she goes, okay, so if I chose to add 5 to this side, but now this side over here, do you agree that it would be unbalanced? I said, yeah, I mean, you got to add 5 to both sides. And so she goes, okay, I could add 5. Okay, fine. So you could get 15 and 15. Okay. And so what she did, she handed out candy. Right? So she handed out candy. She goes, okay, here's 5 pieces of candy, 5 pieces of candy. And we're like, okay. And so it was like Skittle bags. So we just kind of separated them. She goes, you can eat them. And so you're eating all this candy. And she goes, okay. Now, if I decided to do something to one side but not the other, would that cause a problem? So what if I added 10 donuts over here, but I didn't do it to this side of the room? So she handed out 10 donuts to this side of the room only. And then she goes, hey, you can eat them, right? And so the kids started eating donuts. She goes, and I forgot to do it over here. Is that fair? Because that's the property of equality. All right, you're good. And the bell went off. And she goes, she sent you on your way. And I'm sitting on the other side of the room going, do we get any donuts? She goes, no, it's not a fair concept, so good luck. You'll remember that the rest of your life. I was so pissed I don't flip my desk. I wanted a donut. All right, but yeah, it was this concept, right? It still sticks with me because it still enrages me to this day, that you have to do it to the same to both sides. I'm not going to pull that to you guys. That's just cruel and unusual punishment. I'm still enraged by that concept, but I don't forget it. So, all right, but that's the properties of equality. All right, now I'm all hungry. I talk about donuts. All right, let's go to the bottom problem. So we have those the field properties now. So let's do those. Let's scroll down. Okay, so field properties of real numbers. Okay, so we have closure, which I think I put in air quotes substitution, correct? It's not on there? I like to use the word substitution. This property, this first property, I'm going to go in numbers, so I'm doing this first one right here. The closure substitution. This is any time in the middle of a math problem, and you're going to replace a number. So let's say, I had that problem up here earlier where I did something like this. I forgot what I wrote. It was something like this. Okay. All right. And all right, so we knew that we're going to be subtracting these A's, and you're going to be adding the 10 and 6. And suddenly, you replace the 10 and 6, and you replace it with 16. Right? Was 16 was it written on the board earlier?
No,
like this is a new number you just made up. Right? It's brand new. That's substituting. It's adding, subtracting, multiplying, or dividing random numbers together and replacing it with a new number that wasn't already on the board. That's substitution. It could be adding, it could be subtracting, multiplying, or dividing, but it's going to be random numbers. So typically, like on a problem where you'd see something like this, so I'm going to go back to the problem I did here earlier where I had something like this, where I added 4 to both sides, right? And suddenly on this side, you replace it with the 14. That's substitution. It's where you made up a new number that wasn't already previously on the board. Now, the hard part about substitution is knowing when you should put it. It is not used in every step. I have some people, like from previous years, they get too substitution happy and they say, oh, this is substitution, this is substitution, this is substitution. Not every step can be substitution. It's only when you're doing like weird arithmetic. That doesn't happen every time. Sometimes you have to do other things where you move things around. That's other property names. So that's, it's when you do random arithmetic. Okay, Questions with substitutions. Add, subtract, multiply, or divide random numbers. And you're going to replace it with a number that wasn't already on the board previously. I'm going to come back to substitution later. So keep that one in your mind, okay? All right, let's talk about commutative now. I actually did commutative on this problem, I just didn't tell you that. All right. Okay, so next to commutative property, that's the second property, it's right here, this one. Okay, the root word there is to commute. Commute means to move, to group and move. If you commute to work, right? If you commute to work, if you're at a bigger city, you get a bunch of people that are in your same like job, you get in one car, so you carpool and you go to work, right? That's called commuting to work. You're grouping up, you're saving gas. It's a smart thing to do, but you're grouping up and moving. That's what we're doing on this problem. You know, I don't care what was over here. You decided that on a math problem that you were going to group, you know, the 5A and 7A together. You actually have to physically move them so that they're side by side to start your problem. You can't just add across the problem. I know a lot of you have known the shortcuts where you look at a problem and go, oh, that's 6 and 10, that makes 16. Because you commuted them in your head. You knew that you could move them next to each other and then add them later. Now you actually have to physically write that step down. You can't skip anything. If you're going to rearrange, this is the commutative step, where I physically put them next to each other. Does that make sense now? It's like, it's grouping up like terms. That's the best way I can put it. It's to group and move. So if you need to put that little note to yourself, you're going to group and move, that's fine. Group and move. Now, the thing is, that sounds easy enough. It only works for addition and multiplication. Addition and multiplication. Now you're thinking, Ward, you just did it with subtraction. Technically, I'm adding a negative 7A. So it is adding. I can move things around even though it doesn't look like it. It doesn't work for division. It works for multiplication. You can move numbers around all you want. I'll pick very easy numbers. 2 times 3 times 5. Okay. 2 times 3 times 5. What would that be if you were to multiply that out? 30. Okay? 2 times 3 is 6. 6 times 5 is 30. So it is 30. Well, if I just move these around, it's still the same answer. It's still 30. You're just simply rearranging it, right? Because maybe in your problem, grouping it, maybe it was easier figuring out the 10 first, then getting 30. You didn't have to think as hard. As opposed to going, okay, that's 2 times 3, which is 6, times 5. That's a process, right? But this idea of if you want to rearrange the problem, that simple fact that I just move things around, that's commutative. The rest of the stuff is substitution, where I made up new numbers. All right, questions with that? There is a process to doing that. There is a reason why you do that, because maybe your problem has really complicated numbers, and you want to group certain numbers up so they make like nice 10s or 20s, or maybe the decimals or numbers cancel each other out. And so there might be a reason why you ever want to choose to move things around, as opposed to maybe just like terms of variables and stuff where you have to. This is usually a crucial step that some people in algebra class forget. I've definitely seen kids come from Algebra 1 before, and it boggles my mind when they get to a class like geometry and they do a problem like this. Right? Let's say that's their problem. And they go, okay, well that's 6A, and then we add 7A, and that's 13 A's. My brain melts, right? Because this thing didn't have an A on it, so you can't add that, right? It's not a like term. You can rearrange it to be like this, then you can add those two together. And that's like a crucial step that some Algebra 1 kids like miss. I don't know how. It's just like this weird thing where they just see pluses and they don't even see variables. They just add every number together. They don't even think about it. They do just a sum of everything. When you can only do like terms. It's a major crucial step that some Algebra 1 kids come to me and they just lack. It's a lack of attention for detail. They just don't see it. All right, but that's commutative. It is actually useful. I mean, I do it in Algebra 1 a lot when you group things together, but you have to move them first. Then you can do the math later. So I'll come back to that one. Commutative is big later. You'll see that. I'll do an example later on with that. All right, associative. This one's tricky. This one, the word I always put next to associative, maybe you want to write this in your little property sheet. You want to write the word parentheses. So how you spell it looks like parent and then Hesses. So parentheses. This is the parenthesis property. It's used for addition or multiplication, doesn't matter. And it's just simply moving bars around. It's not actually doing math. So let me give you an idea here. Let's say this is your problem. Let's say this is your problem, right? You don't necessarily have to add the ones in parentheses first. I know it seems really goofy. You don't. You can actually move the parenthesis to be in the back around these two, and it would still be the same math problem. You could choose to move the bars because maybe these are easier numbers that you want to do in your head because those cancel out, right? They make 0. And so you know your answer will be 5, like faster than going, okay, that's 11 minus 6. That takes too long, especially with decimals, fractions. I could just cancel stuff out. That's good. Now, it's associative. And you're thinking, okay, well, I wouldn't do that. I can just type it in my calculator. Okay, fair enough. But you do have to do it when you do a problem like this. 4 times 4x. Now you have to move the parentheses bars. Because can I actually multiply a 4 times an x? No. I mean, I don't even know what x is. If I knew what x is, sure, I could plug it in and take 4 times whatever x is. But right now, I don't know what to do with that. I can't do anything. So I have to move the physical bars. I have to move them because the only numbers I can multiply are the 4 times the 4. So that's associative. Now, I will let you know right now, when we do the associative property, it will always, 100% be always after distribution. Distribution, I think it's the 6th property down your page, correct? Mm-hmm. We're going to see that one later. Okay. So you will do the associative 100% after you distribute. So I'll show you that when we get there. So I'm going to come back to number 3 here now. Or 3 here in a minute. Okay, I've been talking a lot. Is there any questions up to this point? Maybe something I glazed over, a question you have, maybe about property sheet or property names? Okay, good. Okay, now we're getting into the kind of tricky territory. There's inverses and identities. I know the names look the same. 4 and 5 are very, very different in property. Okay, the first one is called the identity properties. There is 2. You can see them, I have them listed in red. I think they're italicized in your paper. There's the additive identity, and there's the multiplicative identity. This is the thing I was going to tell you earlier. I said I was going to come back to substitution. I am going to come back to that. But let's talk about the identities. The identity is any time you do some type of math where it doesn't change the outcome of your problem. Okay? So you can do some type of math. So there's 2 types. There's the additive. What is something I can add to a problem that would not change my answer? 0. It's any time. So on a problem, like I have something like this, and I add 0 to it, it doesn't change my problem. It'll be a 5x, whatever it is. So I can add 0 to something. Okay, and I know that seems silly. It's like, why would you ever need to do that? Well, sometimes you need to do that when you actually are in the middle of an Algebra 1 problem like this. And I was solving this problem out, right? That, you know, the rules you've learned, you can add any numbers to both sides, subtract because it's an equation, or it's property equality. Well, you've been taught, okay, you know, add the 4 to both sides, right? You want to identify the side with the x, get rid of the 4 on that side, you want to get the x by itself. So magically add 4. So that's the add property of equality, right? So add prop of EQ. You suddenly showed your work, you're showing that you're adding to both sides. Well, what's 4 and -4 make? 0. It doesn't just cancel out, it makes 0. Okay, well, I should have that makes 0, okay? That's a different property name. But, do you notice that now I have to add 0 to something? That's the additive identity. You add a 0. So now, that allows me to add 0 to an x, which makes just an x. It's the way of getting rid of the 0 in a problem, so that it actually goes. So this is the add identity. It's when you actually physically add the 0. Now, I know that seems weird, because it looks like substitution, correct? Substitution is when you're like doing addition, subtraction, multiplying and dividing random numbers together to make new numbers. The identity is when I actually did addition. Yes, I did addition, but did I make up a new number? No. I mean, I literally just got rid of 0. So it kind of disappeared because this number just repeated. I didn't make up a new number, so it's not substitution. The 0 went away. That's add identity. That's really hard for people to wrap their head around because they're so used to doing substitution for everything that adding 0 is not substitution because it didn't make a new number up. It's the same number just repeated. That's why it's an identity. Now the other type of identity is multiplicative. Multiplicative. The multiplicative identity is the other type of math you can do where you multiply by a number and it doesn't change your outcome. Like 1 times m. Well, 1 times m is just m. Well, you're probably thinking, okay, why would I ever need to do that? Why would I ever need to multiply by 1? You have to do it in an Algebra 1 problem. There's problems that you had to solve and you got 1 out front. And it's nice to get rid of it. So let's say you're doing a problem like this. 5m equals 15. Well, they teach you, you identify the side with the m, you have to do the opposite of this side. So how do I get rid of this 5? Divide, right? You divide by it. That's the division property of the cube. Divide property cube of EQ. All right, I'm showing you I'm dividing to both sides. This side divides out to make 1. That's a different property name. It's not substitution, it's a bit different. And now, at this point, now I'm multiplying by 1. So when I multiply 1 times m, I get m. So it allows me to get rid of the 1. I didn't make up a new number, right? I just simply multiplied by 1. That's multiplicative identity. Or maybe you're in the middle of a problem and you're doing something like this. Maybe that's the middle of your problem. Well, how do I add those m's together? What would I get if I added these m's? 3m. But I couldn't do that yet. Because the reason why? Is there a number in front of my m yet? No, so you have to introduce it. By putting a 1 out front, it's a multi-identity. You just introduce the 1. When you multiply by 1, it doesn't change your answer. So by putting a 1, that allows me to add these later, and eventually I can get to the 3m. Because right now, if I wrote it like that, I don't know what the m is. But by putting a 1 out front, it allows me to add them together to combine my terms. So sometimes it is actually important. I'll show you way different rules for that when you get to like pre-calc and calculus. There's reasons why you ever want to multiply by 1, and they can be insanely hard. We'll see that later. All right, questions with identities. I know that I said earlier, identities will look a lot like substitution. You're using a 1 or you're using a 0, but they go away. They're going away at some point. Okay, inverses. That's probably going to be the one we're going to look at tomorrow. I think I'm going to stop here today. I think we've done enough. So we'll stop at inverses today. We'll do inverses and we'll do distribution tomorrow. And then the goal is tomorrow we'll do a bunch of questions. But that's it today. I think it's a good time to stop. We've been kind of talking a long time.